with a new fancy definition of affine varieties as ring spaces, which are isomorphic to some subset of affine space cut out by polynomial equations. With this new definition, it is actually true that some open subsets of affine varieties are still affine varieties themselves. And that's kind of an important point, summarized in the following proposition, which tells you that, in particular, distinguished open subsets are affine varieties. So if X is an affine variety and F is an A of X, then we have this distinguished open D of F, and the claim is this is an affine variety in our new sense, with coordinate ring given by the localization of AX at F. And for the proof, well, we do have to write D of F in as a closed subset in some affine space. And what we do is we, or more generally, as a closed subset of some other affine variety. And what we do is we take Y to be the set of pairs x comma t in x cross A1, such that t times f of x is equal to 1. This sits inside here, and it is the vanishing locus of this regular function, or this polynomial, because t is the function here, f of x is a function on x, and so this is a well-defined function in here, because you can write it as, I mean, you can use the abstract characterization of this as the tensor product of a of x and a of a1, and then you can write down what element of the tensor product this here corresponds to. So in any case, so this is the well-defined affine subvariety of here, and therefore also an affine variety. And the claim is Y will be the affine variety isomorphic to df. And to do that, we just give a map from Y to df and the map in the opposite direction. The map from Y to df is very simple. You just take this pair and send it to X. So here, if we illustrate this, we have kind of one direction for the X coordinate and one direction for the new T coordinate. And then let's say f of X was given by some function like this. Then Y is the set where T is equal to 1 over F. So basically we see in this picture we would have a pole at the 0 of F. And then the map G is just a projection downstairs. We remember the X coordinate. And the inverse of this map is not hard to write down because it goes from df to y. And since x2, well, the first coordinate must stay the same. And the t coordinate, we just send it to 1 over f of x. And then this clearly satisfies, if you plug in 1 over f of x here, this clearly satisfies this equality. So it is, this here is again a morphism. And in particular, the second component here, this is, of course, a regular function on d of f. We're allowed to divide by f here. And then just as we had it for the very simple function f equals x before, we had a very similar picture. And just the same arguments show that these are inverse to each other. And therefore, d of f is an affine variety in our new sense. And we have already seen that a of d of f, well, this is just the ring of functions on d of f, and that we calculated, it is just the localization of a of x at f. So we get this new kind of affine varieties, which are given by these distinguished open sets and other varieties. Now you could hope, well, the distinguished opens are affine varieties. Maybe just every open subset of a affine variety is an affine variety. Unfortunately, this doesn't work. And the counterexample is, again, an old example that we have seen before. And the claim is that A2 minus 0 is a ring space, certainly, but it is not an affine variety. It's always good to have examples of things which are not the objects that you're looking at. And how would you show this here? Well, for this this set, we have seen that the ring of functions, the ring of regular functions on U is, well, you can compute it as the ring of regular functions on A2 defined on the set U. And this we calculated before. And this here is kind of just the definition of this restriction sheaf. So somehow you compute this restriction sheaf here by just taking the old sheaf and evaluating it at this open set. But that's kind of just general nonsense. And then this was the calculation that we did. So these regular functions are actually all given by restrictions of regular functions on A2, which are just the polynomials themselves. And then from this agreement of coordinate rings, we see if U was an affine variety, the claim is that this here implies that U would have to be isomorphic to A2, and this morphism would have to be given by the identity. That's a contradiction. And if you want to expand this, how does this work? Well, we do have the identity map from U to A2, which is this kind of inclusion. And that map satisfies that its pullback gives an isomorphism of the coordinate rings. Then we had the corollary which said the isomorphisms on one side correspond to isomorphisms on the other side. So this corollary would imply that this here would have to be an isomorphism, but it's not. I mean, it's not even surjective, so it cannot have an inverse map. And so this shows this U cannot be an affine variety. However, I mean, it's still not such a terrible ring space because, for example, it has a cover by these distinguished opens D of x1 and D of x2, which are affine varieties. And so this is one of the things that motivates us in the next chapter to look at more general ring spaces which have open covers by affine varieties. And this will be the abstract varieties of the next chapter.